Tonight, we are going to embark on a journey not measured in miles, but in solitude. A journey that will take us to the very edge of our sun's influence, and even further, into an abyss of stars and time, so vast it defies our imagination. This is a story about the fastest, the farthest, and the loneliest object we have ever built. But at its heart, this is not the story of a machine. It is the story of a feeling. It is the story of an echo of humanity, traveling in silence toward eternity. Have you ever looked up at the sky on a clear night, far from the city lights, and felt overwhelmingly small and alone? It's a universal feeling. The stars, in their cold and distant beauty, remind us of the immensity of the stage upon which we play out our lives. They make us aware of the delicate and almost improbable bubble of life that is our world. In those moments of quiet contemplation, we connect with a question that has haunted our species since we first looked up. Are we alone? And if we could send a message across that ocean of darkness, a bottle cast onto the cosmic shore, what story would we tell about ourselves? This is the story of when we decided to do just that. This is the chronicle of humanity's loneliest journey. Before our traveler leaves the Earth, I would love to know from which part of this small world you are joining us tonight. Write your city or country in the comments, and so, for a moment, we will feel a little less alone in this immensity. And if you enjoy these tales of narrated science, subscribing will allow us to continue exploring together, always calmly, always at the pace of the universe. Our story does not begin in the darkness of space, but here, on Earth. In the year 1977, it is a world that, in many ways, no longer exists. A world without the internet, without mobile phones, where the most powerful computers had less memory capacity than the watch you might wear on your wrist today. It was a time of profound contrasts. The Cold War divided the planet with a palpable tension, but in the realm of science, a sense of optimism. Inherited from the Apollo missions that had taken man to the moon just a few years before, still lingered in the air, humanity felt capable of achieving the impossible. In the halls of NASA's Jet Propulsion Laboratory in Pasadena, California, a group of men and women armed with slide rules, blackboards full of equations, and boundless audacity worked on a project of almost inconceivable ambition. They had discovered a planetary alignment, a rare cosmic ballet that occurs only once every 176 years. A unique opportunity in which Jupiter, Saturn, Uranus, and Neptune would align in such a way that a probe could use the gravity of each planet as a slingshot to propel itself to the next, on a grand tour of the outer solar system. To miss that window would mean waiting nearly 2 centuries for it to appear again. Understanding the magnitude of this mission is key. Our true place in the cosmos, our ability to see beyond our immediate neighborhood, was at risk if we didn't seize this opportunity. The challenge was monumental. They had to build a spacecraft that could survive for more than a decade in the most hostile environment imaginable. The extreme cold, intense radiation, and absolute vacuum of deep space. A craft that would have to make its own decisions, diagnose its own problems, and continue to operate billions of miles from any human help, receiving commands that would take hours to arrive at the speed of light. It had to be, in essence, a robotic extension of human curiosity, autonomous and resilient. They called it Voyager, a simple name, yet laden with profound meaning. It was not a conqueror. It was not a weapon. It was simply a traveler, and its purpose was to see, to measure, to learn, and above all, to continue. 2 twin probes were built, Voyager 1 and Voyager 2. Voyager 2 was the first to depart, on August 20th, 1977, on a slower but safer trajectory designed to visit all 4 giant planets. A few weeks later, on September 5th, it was Voyager 1's turn. Its path would be faster, a direct route to Jupiter and Saturn, which would catapult it out of the plane of the planets, toward the galactic north, into the unknown. Imagine that day, the Florida sun shining on Launchpad 41 at Cape Canaveral. Atop the steel structure stood the Titan Centaur rocket, and at its apex, protected like a precious jewel, was Voyager 1, a 722-kilogram machine with its large 3.7-meter diameter antenna pointing to the sky, ready to become the ear and voice of humanity. Its scientific instruments, its cameras, its magnetometer mounted on a long bow to keep it away from the interference of the craft itself. Everything was ready. Its heart was not an engine, but a radioisotope thermoelectric generator, a nuclear power source that would allow it to keep running for decades, long after the sun's light became just another bright star in its sky. At 8:56 in the morning, local time, the engines roared to life. The launch was not a violent explosion, but a controlled and majestic ascent, a pillar of fire and smoke that for an instant united the earth with the heavens, pushing the small traveler beyond the blue atmosphere that had seen it born. For the scientists who had dedicated years of their lives to this project, it was a moment of unbearable tension and hope. They had calculated every trajectory, foreseen every risk, but from that moment on, their creation was on its own. Its journey beyond home had begun. As it ascended, higher and higher, faster and faster, it shed the stages of its rocket, freeing itself from the gravitational bonds of its mother planet. Soon, it was just a point of light, beginning a path that would take it farther than any other object had ever gone before. It was leaving behind the only world it had ever known, to become a lonely pilgrim in the silent cathedral of the solar system. Its journey, our journey, had only just begun. Once free from Earth, Voyager 1 began to experience the true meaning of space. The vibrant blue of its home world faded behind it, shrinking until it became a gleaming marble, accompanied by its pale companion, the moon. For the first time, the probe's cameras captured an image of the Earth and moon together in a single frame, a family portrait taken from the edge of the abyss. It was a perspective no human had ever seen directly, that of a child moving away from home and looking back to see the place that holds everything, now reduced to a simple object in the sky. The mission's solitude became tangible in that first image. It was no longer a part of Earth. It was a distant observer of it. The sun became the dominant presence, not as the warm sphere we know, but as a disk of silent white fury against a backdrop of absolute blackness. Its light, without an atmosphere to scatter it, was raw and sharp, casting harsh shadows on the probe's body. But more important than its light was its invisible breath, the solar wind, a constant stream of charged particles flowing from the solar corona at millions of miles per hour. Voyager's instruments began to measure this flow, to feel the pulse of the sun, learning about the environment it would have to navigate. This wind would be its constant companion for years, a current in the ocean of night that would subtly push it on its way. Meanwhile, on Earth, in the dimly lit control rooms of JPL, the mission entered a new phase. The drama of the launch was over, and now began the long, patient vigil. Communication with Voyager was a dialogue across a growing abyss. Engineers sent commands like whispers through the parabolic antennas of the Deep Space Network, and they waited. They waited for minutes, which would soon become hours, for the probe's response, a stream of binary data, to return to them. They listened for the heartbeat of the craft, the telemetry reporting its temperature, its power consumption, the status of its systems. Each packet of data was a sigh of relief, a confirmation that their traveler, their extension into the cosmos, was still alive and well. The first great challenge of the journey lay a few 100 million miles from home, the asteroid belt. Situated between the orbits of Mars and Jupiter, this vast ring of cosmic debris has captured the popular imagination as an almost impenetrable barrier, a dense field of violently colliding rocks. The reality, as is often the case in space, is much stranger and emptier. Although there are millions of asteroids in the belt, from dust grains to bodies the size of small countries, the volume of space they occupy is so immense that the average distance between them is over 1 million miles. The probability of Voyager colliding with a large asteroid was infinitesimally small. However, the danger was not the spectacular collision we see in movies. The real risk was the unknown, the dust and countless microscopic particles that could, at the probe's incredible speed, act like a sandblaster, damaging delicate instruments or puncturing vital components. The asteroid belt was less a minefield than a desert filled with ghosts, the remnants of a planet that never formed, a silent cemetery of the primordial bricks of the solar system. For months, Voyager 1 sailed through this region. The mission controllers held their breath, metaphorically speaking, as their creation ventured into the first truly alien territory. On December 8, 1977, the probe emerged unscathed on the other side. It had passed its first test. The door to the outer solar system was officially open. As it left the belt behind, the environment changed. The lonely traveler was now entering the realm of the giants. Its first destination, Jupiter, was still hundreds of millions of miles away, but its presence was already beginning to be felt. Jupiter is not just a planet. It is almost a miniature solar system. Its mass is more than double that of all the other planets combined, and its gravitational influence is immense. But even more impressive is its magnetic field. Jupiter's magnetosphere is the largest structure in the solar system, after the Sun's own heliosphere. It is a magnetic bubble so gigantic that if we could see it in our night sky, it would appear several times larger than the full moon. Long before Voyager's cameras could distinguish Jupiter as more than the brightest star in its sky, its particle instruments began to detect the first whispers of this monstrous magnetosphere. It was feeling the giant's breath. As it drew closer, day after day, week after week, the planet's image began to transform. The bright point of light became a small disk. Then, the disk grew, filling more and more of the camera's field of view. Colors began to appear. Bands of clouds in shades of ochre, orange, and white. The probe was approaching a world so different from Earth, it might as well belong to another star. A world with no solid surface, an ocean of hydrogen and helium thousands of miles deep, ruled by storms that last for centuries. The solitude of Voyager's journey was about to be interrupted, not by friendly company, but by the overwhelming and chaotic presence of the king of the planets. The calm of interplanetary space was giving way to an environment of intense radiation and turbulent magnetic forces. For the small probe, it was as if a sailboat that had crossed a calm ocean was about to enter a perpetual hurricane. The solitary traveler had arrived at the king's court, and it was about to awaken its secrets. Humanity, through the eyes of its brave emissary, was about to see Jupiter as it had never been seen before. The true exploration was about to begin. The lonely traveler was now crossing the invisible threshold of Jupiter's kingdom. This boundary is not a line in space, but a turbulent region known as the bow shock. It is the place where the constant wind from the sun, which had accompanied Voyager for over a year, violently collides with Jupiter's colossal magnetosphere. For the probe, it was as if the gentle murmur of deep space suddenly turned into the roar of an invisible waterfall. Its instruments recorded a drastic change in the nature of the particles, in the direction and strength of the magnetic fields. It had officially entered the giant's domain, an environment governed not by the sun, but by the overwhelming power of Jupiter itself. From this moment on, every piece of data it sent back to Earth would be a revelation, a glimpse into a world that until then we had only been able to admire as an enigmatic point of light in our telescopes. As it plunged deeper into this magnetic ocean, the planet grew in its field of view until it occupied the entire frame. The sight was hypnotic. Jupiter has no solid surface to land on. It is a sphere of gas and liquid that extends for thousands of miles toward a dense, mysterious core. What we see are only the tops of its clouds, a planetary canvas of turbulent and dynamic beauty. Bands of colors, known as zones and belts, stretched from horizon to horizon, flowing at different speeds and in opposite directions. They were rivers of ammonia clouds and other chemical compounds, painted in shades of cream, ochre, and sienna by unknown elements rising from the depths. Between these bands, the atmosphere seethed with activity. Vortices and eddies the size of continents spun like gears in a cosmic machine. Some white, others brown, all indicative of a weather system on a scale and of a violence that dwarfs any terrestrial storm. And amidst all that organized chaos was the planet's most iconic feature, the Great Red Spot. It was not merely a spot, it was an eye, a stormy, crimson eye that has been watching the solar system for at least the 300 years we have been observing it from Earth. Voyager 1 provided us with the first close-up, detailed look at this meteorological monster. It is an anticyclonic storm, a hurricane so immense that it could swallow our entire planet 3 times over with ease. Its clouds rotate counterclockwise, completing a turn every 6 days, with winds at its edges exceeding 400 kilometers per hour. Far from being a simple surface phenomenon, the spot is a structure deeply rooted in the Jovian atmosphere. To see it up close, through the eyes of Voyager, was like peering into the heart of a planetary forge, a place of power and permanence that defied our understanding of weather. But Jupiter's atmosphere held more secrets. At night, on the unlit side of the planet, the probe's instruments detected flashes of light, lightning. These were not mere sparks, but superbolts, electrical discharges hundreds of times more powerful than any that occur on Earth, illuminating the depths of the water clouds believed to exist far below the visible layers. Voyager confirmed that Jupiter, like Earth, is an electrically active planet, but on a scale that could only be described as titanic. And amidst this violent beauty, the small probe, a fragile creation of Earth, continued on its path, recording, measuring, and transmitting, a silent witness to the majesty of the king. However, the real shock, the revelation that would forever change our view of the solar system, came not from the planet itself, but from its court of moons. Voyager 1 focused on the 4 large Galilean satellites, worlds as large as planets themselves. The first to reveal its secrets was Io. From Earth, it was just a point of light, but as Voyager approached, the image focused on a world of nightmare and wonder. Its surface was not gray and cratered like our moon, but a chaotic palette of yellows, reds, oranges, and blacks. It looked like a cosmic pizza, mottled and strange. The reason for these colors became apparent in one of the most important images in the history of space exploration. While analyzing a photograph of Io's limb, a navigation engineer named Linda Marabito noticed a strange umbrella-shaped protuberance extending from the surface into space. It was not a cloud. It was not a flaw in the image. It was the plume of a volcano in full eruption. For the first time in history, we had discovered active volcanism outside of Earth. Io was not a dead frozen world. It was the most geologically active body in the solar system. Voyager detected 9 ongoing volcanic eruptions, some spewing material more than 300 kilometers high. This volcanic hell is the result of a gravitational tug-of-war. The immense gravity of Jupiter and the influence of the other Galilean moons constantly stretch and squeeze Io, heating its interior into molten rock. This discovery was a paradigm shift. It showed that worlds didn't need to be as large as Earth to have geological activity. Tidal energy could be a motor as powerful as a planet's internal heat. Next, Voyager turned its gaze to Europa. And again, astonishment. If Io was a world of fire, Europa was a world of ice. Its surface was incredibly smooth, almost devoid of impact craters, suggesting it was geologically very young. It was crisscrossed by a complex network of reddish lines and cracks, like the veins of an eyeball or the scars on ancient porcelain. The simplest and most powerful picture that emerged from these observations was that of a crust of water ice floating on an internal ocean of liquid water. The idea of an extraterrestrial ocean, right here in our solar system, was electrifying. If there is a place in the universe where life could exist beyond Earth, an ocean of liquid water under a protective ice shell is one of the most promising candidates. Voyager 1 couldn't prove its existence, but its images planted a seed, a question that has driven entire missions since. What lies beneath Europa's ice? The lonely traveler had unveiled the innermost secrets of the stormy king's court. It had witnessed the power of its atmosphere, the hell of Io, and the icy promise of Europa. And even as it departed, it made one last discovery: a ring, a faint, tenuous ring composed of dust, invisible from Earth, a secret the giant had guarded jealously. After only a few months, the encounter was over. Jupiter's gravity, which had pulled the probe towards it, now flung it away with even greater speed, acting as the cosmic slingshot its creators had foreseen. The encounter had been an overwhelming success. The king had revealed its treasures, but the lonely pilgrim's journey was not yet over. Now, in its wake, a new destination was drawn: the Lord of the Rings. The encounter with Jupiter had been a whirlwind of discoveries, an assault on the senses of the small probe and its creators on Earth. But as quickly as it began, it ended. Propelled by the gravitational pull of the giant planet, Voyager 1 was launched like a stone in a cosmic slingshot, accelerating to a speed of over 60,000 kilometers per hour on a precise trajectory towards its next target. Behind it, Jupiter and its court of moons began to shrink. The crimson eye of the Great Red Spot faded into the tapestry of clouds, and the moons, which for a brief moment had been individual worlds full of wonder and promise, became mere points of light again. The roar of Jupiter's magnetosphere subsided, and the probe plunged back into the relative silence and calm of interplanetary space. Solitude returned, but it was a different kind of solitude. The traveler was no longer a novice. It had survived its first encounter with a monumental, and now it carried with it the secrets it had wrested from the king. On Earth, the mission team breathed a sigh of relief. Voyager had survived Jupiter's intense radiation belt, an environment so hostile it could have fried its circuits and blinded its cameras forever. Now began a period of analysis and patient watchfulness. Engineers ran exhaustive diagnostics, sending command sequences across the abyss to check the health of every instrument, every system. They listened intently to the telemetry, the electronic pulse of their creation, looking for any sign of damage or degradation. It was a testament to the incredible engineering of the probe that, despite having received a radiation dose hundreds of times higher than what is lethal to a human. Its main systems were still functioning perfectly. It was wounded, but alive and ready to continue its odyssey. Now it faced the longest leg of its scheduled journey. The distance between Jupiter and Saturn is immense, over 650 million kilometers, a void so large it is difficult to comprehend in human terms. At Voyager's speed, this journey would take almost 2 years. 2 Earth years of traversing through largely empty space. For the probe, time became an abstract concept. There was no day or night. Only the constant glare of the distant sun and the slow procession of the constellations. Its routine was monotonous. Measure the solar wind, count cosmic rays, keep its antenna pointed at an Earth that was already invisible to the naked eye. It was the equivalent of a lone ship crossing the largest imaginable ocean, seeing no land for months, relying solely on its instruments to know it was still on course. Communication with its home became increasingly ethereal. The distance grew with every second. When Voyager left Jupiter, a radio signal, traveling at the speed of light, took about 40 minutes to reach it. By the time it approached Saturn, that waiting time had doubled. Every conversation was an exercise in extreme patience. An engineer in California would send a question and have to wait nearly 2 hours for the answer. They were talking to the past. They were piloting a ghost. This growing delay reinforced a fundamental truth of the mission. Voyager had to be smart. It had to be autonomous. Its onboard computers, though primitive by our standards, were programmed with sequences that allowed it to take care of itself, react to unforeseen problems, and execute its scientific observations without constant supervision. It was a true robotic explorer, making decisions over 1 billion kilometers away from its creators. But the space between planets is not completely empty. It is a desert, but a desert filled with subtle phenomena. Voyager continued its silent work, mapping this uncharted territory. It measured how the solar wind expanded and cooled as it moved away from its source. It detected the flux of elusive cosmic rays, high-energy particles from distant supernovae, and other cataclysmic events in the galaxy. This data, while not generating spectacular headlines like photos of volcanoes on Io, was pure gold for scientists trying to understand the structure of our solar system. It was the patient science of exploration, the slow, meticulous work of drawing a map where before there was only a blank space. Every bit of information was a new brushstroke in our portrait of the cosmos. And as the months turned into years, a new point of light in its personal firmament began to grow in importance: Saturn. At first, it was just a bright star that didn't twinkle. Then, as Voyager devoured the kilometers, that star began to resolve into a disk of a pale yellow color, serene and elegant. And then the feature that defines it, what makes it the most recognizable object in the night sky, appeared: its rings. At first, through the probe's cameras, they looked simply like handles or extensions on either side of the planet, just as Galileo Galilei had first drawn them in the 17th century. But as it got closer, those handles separated from the planet, reviewing themselves as an independent structure, an incredibly thin and wide disk surrounding the planet's equator. The anticipation at JPL was palpable. Jupiter had been a world of raw power and chaos. Saturn promised something different. It promised beauty, order, and a more subtle mystery. The questions were countless. What were the rings made of? Were they solid? Were they a cloud of particles? How many were there really? And what secrets did the moons orbiting within and beyond them hold? The lonely traveler, after its long and monotonous journey across the interplanetary desert, had arrived at a new and exotic oasis. The chaos of Jupiter was behind it, replaced by a promise of ordered and cold beauty. The encounter with the Lord of the Rings was about to begin. The encounter with Saturn was like shifting from a thundering symphony to an intricate and mathematically beautiful piece of chamber music. If Jupiter was a king of chaotic and overflowing power, Saturn was a monarch of cold, ordered elegance. As Voyager 1 dove into its system, the planet grew into a serene orb of pastel colors, a perfect sphere of yellow, gold, and white hues, far more subtle and less turbulent than its older brother's atmosphere. Although it also possessed fierce winds, among the fastest in the solar system, reaching 1,800 kilometers per hour at its equator, its appearance was one of majestic calm. The cloud bands were softer, the vortices less defined, all veiled by a layer of haze that gave it an ethereal and diffuse look. It was the very image of planetary serenity. But the true marvel, the center of all attention, was the rings. From Earth, even with the best telescopes, the rings appeared to be 3 or 4 solid concentric disks, separated by dark gaps, like the grooves of an old vinyl record. They had been given simple names, A, B, C, D. But what Voyager 1 revealed as it drew closer was a paradigm shift as profound as the discovery of Io's volcanoes. The rings were not solid disks. They weren't even a few hundred. They were thousands. Tens of thousands of individual ringlets, each composed of countless particles of water ice, ranging from the size of a dust grain to that of a house, all orbiting together in an incredibly thin disk, just a few tens of meters thick in most places, but stretching for hundreds of thousands of kilometers. The images the probe sent back to Earth were hypnotic, a display of structural complexity that no one had anticipated. We saw that the main rings were composed of thousands of thin ringlets, some perfectly circular, others eccentric. We saw density waves propagating through them like ripples in a pond, caused by the gravitational influence of nearby moons. We saw dark, radial structures, like the spokes of a bicycle wheel, that appeared and disappeared in a matter of hours, defying the known laws of orbital physics. And we discovered rings that seemed to be braided, like strands of a cosmic rope, a baffling phenomenon later explained by the influence of 2 small shepherd moons that, with their gravity, confine and shape the ring particles between them. It was the revelation that Saturn's ring system was not a static, dead structure, but a dynamic ecosystem, a river of ice in constant change, shaped by gravity, collisions, and forces that we still don't fully understand today. Voyager 1 acted as a cosmic microscope, showing us that the simplicity we saw from afar was in reality a near-infinite complexity up close. The traveler's solitude was rewarded with a view of one of the most exquisite spectacles the solar system has to offer. It was as if nature had decided to write the laws of orbital physics in the most beautiful form possible. But Saturn's system is much more than its rings. Like Jupiter, it possesses a vast court of moons, each a unique world with its own story. Voyager 1 performed flybys of several of them. We saw Mimas with its gigantic Herschel impact crater that gave it a striking resemblance to the Death Star from science fiction. We observed Enceladus, a world covered in incredibly bright and reflective ice, as white as freshly fallen snow, hinting at a young and geologically active surface, a seed of mystery that future missions would explore. We saw Tethys, with its enormous canyon that stretched 3/4 of the way around its circumference, a scar from a violent past. Each moon was a piece of the puzzle, a testament to the diversity of worlds that can exist in orbit around a single planet. However, there was one moon that was the primary objective of the mission of Saturn, a moon that alone justified the journey and would determine Voyager 1's ultimate fate. Its name was Titan. It is the largest moon of Saturn and the second largest in the solar system, even larger than the planet Mercury. But its size was not its most intriguing feature. Titan is the only moon in our solar system to possess a dense atmosphere, even denser than Earth's. From afar, it is a mysterious, opaque orange sphere, completely veiled by a haze of organic hydrocarbons. We could not see its surface. It was a veiled world, a secret wrapped in an atmosphere rich in nitrogen and methane. Scientists were desperate to know what lay beneath that veil. Conditions on Titan resembled in some ways those of the early Earth, before life arose and filled our atmosphere with oxygen. Studying Titan was like looking through a window into our own planet's deep past. To do so, Voyager 1 had to perform a very close flyby, a maneuver that would take it under the moon's south pole. This trajectory, however, came at a price. Titan's powerful gravitational pull would act as a final slingshot, but this time it would not send it toward another planet. It would fling it upwards, out of the plane of the ecliptic, the flat plane on which all the planets orbit. It would take it off the Grand Tour forever and set it on an escape trajectory from the solar system. The decision had already been made. The knowledge to be gained from Titan was deemed more valuable than the chance to visit Uranus and Neptune, a journey that would, in any case, be left to its sister probe, Voyager 2. On November 12, 1980, Voyager 1 dove into its final encounter with a planetary world. It passed just 4,000 kilometers from the tops of Titan's clouds. Its instruments analyzed the atmosphere's composition, measured its temperature and pressure. They discovered it was composed mainly of nitrogen, like ours, but rich in methane and other organic compounds. The data suggested an incredibly exotic world with a methane cycle that mimics Earth's water cycle. Methane clouds, methane rain, and rivers, lakes, and seas of liquid methane on its surface. A frozen world, yet astonishingly familiar in its processes. The lonely traveler had lifted a corner of Titan's veil, revealing a landscape that surpassed science fiction. And in doing so, it sealed its fate. The giant moon's gravity took hold of it and hurled it toward the galactic north in a one-way journey to the stars. Its primary mission was over. It had more than fulfilled its purpose. It had revealed the secrets of Jupiter and Saturn in a way that forever changed the textbooks. But its journey, the true lonely journey, was just beginning. It was leaving behind the last known port, the last world with an atmosphere, and heading into the twilight of the solar system on its long, slow goodbye. The encounter with Titan was the kiss of farewell. The gravitational pull of the giant moon, a maneuver calculated with astonishing precision, acted as the final slingshot. But unlike the boost from Jupiter, which had kept it on the carousel of the planets, this push sharply diverted it from its path. Voyager 1 began to ascend, rising above the plane of the ecliptic, that flat cosmic disk on which all the planets, from Mercury to Neptune, trace their orbits around the Sun. It was a profoundly symbolic move. Throughout its mission, it had been a horizontal traveler, moving from one world to another on the same plane. Now, it was rising, taking a spectator's perspective, like someone getting up from their seat in a theater to see the entire stage from above. Behind and below it, Saturn and its rings shrank, becoming the last great spectacle, the last jewel it would see up close on its endless journey. With its planetary mission concluded, the probe could have been considered a success and simply been monitored until its eventual silence. But at NASA, the mission was reborn with a new name and an even grander purpose: the Voyager Interstellar mission, VIM. Its objective was no longer to photograph worlds, but to test the boundaries of the Sun's domain. It became an explorer of limits, an outpost sent to study the unknown environment where our star's influence ends and true interstellar space begins. The lonely traveler had received a new commission to be humanity's first ambassador to the galaxy. Its journey, far from over, had become infinitely longer and deeper. The 1980s passed in almost absolute silence for the probe. It was a decade of slow, patient traversing through the outer suburbs of the solar system, a time of unimaginable solitude. The sun, once an overwhelming presence, shrank in Voyager's sky until it became the brightest star, but a star nonetheless. Its light, though still powerful, arrived increasingly weakened, and the probe depended entirely on the heat generated by its plutonium heart to prevent its electronic components from freezing in the near absolute zero cold. The great planets that had been its dance partners were now mere points of light in the distance, indistinguishable from distant stars, except for their steady movement and lack of twinkling. The solar system, the place we call home, was dissolving into the tapestry of the Milky Way. On Earth, time also passed. The scientists and engineers who had built and launched Voyager grew older. Some retired, others passed away. A new generation of mission controllers took over, people who were children when the probe began its journey and who were now the guardians of its legacy. Communication became an act of faith. The light travel time stretched to hours. Sending a command and receiving confirmation could take the better part of a workday. This monumental delay created a strange disconnect. The team on Earth lived in the present, but worked with the probe's past, sending instructions to a place where Voyager would no longer be when they arrived. The ship's loneliness was mirrored in the growing temporal distance that separated it from its creators. It was in the midst of this long, dark journey that an idea emerged, an idea that was not purely scientific, but deeply philosophical and poetic. It came from the astronomer Carl Sagan, a key member of the Voyager imaging team and a visionary who understood science not just as a collection of data, but as a tool to expand human perspective. Sagan realized that Voyager 1 was in a unique position in space and time. From its elevated vantage point, looking down on the solar system, it had the opportunity to do something no other craft had done. Take a family portrait of the planets, including our own, from the outside. The proposal, however, met with considerable resistance. For many at NASA, Voyager's primary mission was over. Its cameras, designed for the relatively bright light of Jupiter and Saturn, were not sensitive enough to capture quality images of distant and dimly lit worlds. Worse, to take the picture of Earth, the camera would have to point very close to the sun, risking that direct sunlight would damage its sensitive detectors and leave it blind forever. It was argued that it was a risky maneuver, with no clear scientific value, and an unnecessary use of the mission's limited resources and the Deep Space Network's time. It was a battle between pragmatic engineering and poetic sentimentalism. But Sagan was persistent. For years, he championed the idea. He argued that the value of the photo lay not in the details it might reveal about the planets, but in the perspective it would offer about ourselves. Seeing our world as a simple point of light, he argued, would be a lesson in humility and a powerful statement about our place in the cosmos. Finally, after much deliberation, his vision prevailed. NASA gave the green light for Voyager 1's final photographic assignment. The chosen day was February 14, 1990. Nearly 6 billion kilometers from home, in the deep darkness beyond Neptune's orbit, Voyager 1 received its orders. The command sequence, carefully crafted over months, reached the probe after a 5.5-hour journey at the speed of light. And then, the lonely traveler which for a decade had kept its gaze fixed on the darkness ahead, began to slowly turn. Its camera platform moved, pointing back towards the heart of the solar system it had left so long ago. Over the next few hours, it executed a series of 60 exposures, capturing a mosaic of images that included Neptune, Uranus, Saturn, Jupiter, Venus, and, of course, Earth. It was the first and only portrait of our solar system taken from the outside. The camera shutters opened and closed in the absolute silence of space, capturing photons that had traveled for hours from their homeworlds. Once the sequence was complete, the data began its long journey back. The images were on their way, encoded in a faint radio signal stretching across the solar system. No one at JPL knew for sure if the camera's sensitive detectors would have survived, or if the pale light of the planets would be more than an undetectable blur in the cosmic noise. All that was left was to wait, as the last self-portraits of our solar system traveled home on a radio thread, carrying the most distant photograph ever taken. At the Jet Propulsion Laboratory facilities, the atmosphere was one of contained anticipation. For 5.5 hours, the data had traveled through space, weakening with every kilometer. Finally, the gigantic antennas of the Deep Space Network, our ears on the cosmos, picked up the signal. It was incredibly faint, a needle of information in the haystack of cosmic noise. But it was there. The data began to flow, bit by bit, into the computers at JPL. It wasn't like downloading a photograph today. It was a slow, meticulous process, a trickle of numbers representing the light levels captured by each pixel of Voyager's camera. Each number was a treasure, a photon that had completed a journey of billions of kilometers to tell a story. Over the next few days and weeks, image processing specialists worked to assemble the puzzle. They had 60 frames, most of them showing little more than empty black space. Their task was to navigate this atlas of darkness to find the tiny points of light they knew must be there, the planets. One by one, they located them. Jupiter, still majestic even at that distance. Saturn, its rings barely discernible. Uranus and Neptune, pale and ghostly at the icy edges. Venus, bright and close to the sun. It was the family portrait Carl Sagan had dreamed of, a composition that showed our solar system in its true scale, a handful of small, scattered worlds in an overwhelming immensity. And then they looked for the most important one. They looked for Earth. They found it within one of the bands of scattered sunlight, a camera artifact from pointing near the sun. And what they saw was, at first glance, almost disappointing. It was not a blue and white globe. It was not a disk. It was a point. A single pixel of pale light, so small and inconspicuous, it could easily be mistaken for a speck of dust on the lens. They called the image the pale blue dot. Earth, our home, had been reduced to 0.12 pixels. Everything we are, everything we have ever been, captured in a fraction of a point of light. The image, technically imperfect and of little scientific value, was nevertheless the most important photograph ever taken. It was then that the true revelation of the mission, its philosophical climax, became apparent. The realization that Voyager's most important discovery was not a volcano on Io or a braided ring at Saturn, but the perspective it gave us on ourselves. Carl Sagan, upon seeing the image, wrote the words that would immortalize it, and that summarize the ultimate meaning of Voyager's journey. He invited us to look again at that dot. Consider what it represents. On that mote of dust suspended in a sunbeam is everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that, in glory and triumph, they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit, yes. Settle, not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. This was the true climax of Voyager's journey, the revelation that its exploration of the outside was ultimately a lesson about our inside. The image became a cultural icon, a powerful symbol for environmentalism, and a perpetual reminder of our fragility and our unity. Sagan's poetic gesture had turned out to be the most profoundly scientific act of all, because it changed the way we see ourselves. Shortly after capturing this final portrait, on February 14, 1990, JPL engineers sent one last command to Voyager 1's cameras: power down. Power was too precious to be spent on instruments that no longer had anything to photograph. The darkness ahead was uniform and would not change. Voyager's photographic mission was over. Its eyes closed forever. It had fulfilled its promise. It had shown us the worlds of our solar system. And finally, it had shown us our own. Now, blind but with all its other senses alert, it would continue its journey, venturing ever deeper into the night, carrying the image of our home in its digital memory and in ours. Its time as a photographer was over. Its time as an interstellar messenger was just beginning. The act of turning off Voyager 1's cameras was a profound transition. It marked the end of its mission as a photographer, as a tourist in the spectacular worlds of our solar system. But it inaugurated a new era, transforming it into a pure explorer, a probe that would no longer be dedicated to seeing things in space, but to feeling the texture of space itself. Its journey ceased to be about destinations and became about exploring the path itself. A path that would lead it through the vast protective sphere of our sun's influence, a region known as the Heliosphere. To understand the rest of Voyager's journey, we must imagine this Heliosphere. It is not the empty space we often conceive. It is a colossal bubble, inflated by the incessant breath of our star, the solar wind. Inside this bubble, everything is bathed in the sun's particles and magnetic fields. It is our cosmic home in the broadest sense, the sun's domain. Outside this bubble lies the interstellar medium, the raw material of the galaxy, forged by other stars and other suns. Voyager 1's new and grand mission was to travel through this bubble, measure its properties to its very edge, and, if it survived long enough, be the first human object to pierce it and taste the air of the galactic ocean beyond. Thus began the years of the Great Crossing. The 1990s and the early years of the new millennium were a period of slow, patient journeying through an invisible desert. For the blind traveler, the landscape did not change visually, but its other instruments painted a picture of a dynamic and subtle environment. Its cosmic ray detector acted like a shield, measuring the high-energy particles trying to penetrate the heliosphere from the galaxy. Its magnetometer sensed the ripples and folds of the sun's magnetic field, which extends in a vast spiral as the star rotates. And its plasma wave detector listened to the hiss and crackle of the solar wind particles as they passed. The probe had become a buoy in a cosmic ocean, recording the tides and currents of an invisible sea. On Earth, the distance continued to grow, stretching the thread of communication to its limit. The probe's solitude manifested in time. By the year 2000, a round-trip message took over 18 hours. The mission team sent commands to a craft that would no longer be there when they arrived, and received data describing an event that had occurred 9 hours earlier. It was a dialogue with an echo, a conversation with time itself. On February 17, 1998, Voyager 1 reached a milestone of profound resonance. At a distance of 10.4 billion kilometers, it surpassed another probe, Pioneer 10, to officially become the most distant human-made object from Earth, a title it has held ever since and will continue to hold indefinitely. Every day that passed, it set a new distance record, venturing ever deeper into a territory where nothing and no one from our world had ever been before. For years, scientists watched Voyager's data, waiting for a sign, a change in the environment that would tell them they were approaching the edge of the heliosphere. Theory predicted that there would be a first major frontier, a region called the termination shock. This is not a physical wall, but an invisible shockwave. It is the place where the solar wind, which has traveled at supersonic speeds, over 1 million kilometers per hour since leaving the sun, finally collides with the pressure of the interstellar gas and abruptly slows down, becoming denser, hotter, and more turbulent. Predicting its exact location was impossible. Scientists could only wait and watch the data, like a sailor scanning the horizon for the first sign of land. For years, the solar wind measured by Voyager remained remarkably constant in its speed. But in mid-2002, the data began to get strange. The instruments detected bursts of particles that seemed to flow back, as if they had hit an invisible wall and bounced off. The probe was feeling the breath of the frontier ahead. The anticipation in the scientific community was immense. And then, in December 2004, it happened. The data that arrived on Earth after its long journey showed an unmistakable and dramatic change. The speed of the solar wind had plummeted. The strength of the magnetic field had skyrocketed. The temperature of the gas had increased. There was no doubt. At a distance of nearly 14 billion kilometers from the Sun, Voyager 1 had crossed the termination shock. This was a historic moment, a re-engagement in the long narrative of the probe. It had entered the final and strangest layer of the heliosphere, a region known as the heliosheath. If the heliosphere is a bubble, the heliosheath is its foamy, turbulent skin. It is a chaotic transition zone where the solar wind, now slow and compressed, is deflected and flows towards the tail of the heliosphere, like water from a river hitting the sea. The blind traveler had crossed the first boundary. It had left behind the inner realm of the sun, the predictable flow it had known for 27 years, to enter its turbulent final frontier. It was no longer sailing a river, but the rapids that precede the great waterfall into the interstellar ocean. The final frontier, the heliopause, was closer, but the path through this new and chaotic territory would be the longest and most mysterious of all. The probe, solitary and blind, now had to navigate the foam of the solar sea, feeling its way towards the shore of the galaxy. Entering the heliosheath was as if our lonely traveler, after having navigated an immense and predictable river, had reached a turbulent estuary where the fresh water of its river collides with the salty tide of the ocean. The environment changed completely. The constant and relatively orderly flow of the solar wind disappeared, replaced by a chaotic sea of slow, hot, and compressed particles. Voyager 1 now found itself in the skin of the solar bubble, a transition zone where the last gasps of the sun's breath fought against the immense and silent pressure of interstellar space. For scientists on Earth, this was the most exciting region. Their theoretical models were about to be put to the test. They thought they understood what this frontier would be like, but, as often happens in true exploration, reality turned out to be much stranger and more wonderful than the prediction. The years began to pass. 2005, 2006, 2007. The probe ventured deeper and deeper into this new region. The models had suggested that the heliosheath would be relatively thin and that Voyager would cross it in a few years to emerge into interstellar space. But the probe kept traveling, and the data it sent back continued to show that it was firmly within this zone of turbulence. Year after year, the final frontier, the heliopause, seemed never to arrive. This presented a fascinating puzzle. Our sun's bubble was much larger, more robust, and more complex than anyone had imagined. Voyager's lonely journey was not just mapping unknown territory, it was forcing scientists to redraw the maps entirely. We were discovering the true size and nature of our cosmic home. While navigating this turbulent sea, the probe made a discovery that perplexed scientists. They expected the magnetic field in this region to be chaotic and disorderly. Instead, in certain places, Voyager found something totally unexpected, a kind of calm in the midst of the storm. It discovered regions where the sun's magnetic field lines somehow connected with the lines of the interstellar magnetic field, creating tunnels or passageways. They called them magnetic highways. These were not physical structures, but regions where particles could flow much more easily between the inside and outside of the heliosphere. Imagine two networks of threads, one from the sun and one from the galaxy, that suddenly intertwine and merge at certain points. Through these connection points, hot, low-energy particles from the solar system could escape into the galaxy, and cold, high-energy particles from the galaxy. The cosmic rays could enter. The boundary of our solar system was not an impenetrable wall. It was a porous and dynamic membrane, a place where two distinct cosmic environments mixed and breathed together. Voyager was found to be traveling through these magnetic portals, with one foot in the solar system and one in the galaxy. It was an astonishing revelation that demonstrated how interconnected our small corner of the universe is with the rest of the cosmos. Time continued to pass on Earth. The Voyager mission celebrated its 30th anniversary, then its 33rd. The children who had been born on the day of its launch were now adults with their own families. And the probe, the relic of the 1970s, kept working, kept sending its whispers from the frontier. The mission team watched the data with almost geological patience, waiting for two key signals that would announce the impending final crossing. The first would be the near total disappearance of solar wind particles, the last breath of its mother star. The second would be a massive and sudden increase in the amount of galactic cosmic rays, the roar of distant stars. Starting in 2010, the data began to show tantalizing signs. There were periods of days, sometimes weeks, when the flow of solar particles decreased dramatically and cosmic rays increased, as if Voyager had stuck its head out of the bubble, only to be swallowed by it again. These false exits showed that the boundary was not a smooth, perfect line, but a turbulent and undulating surface. Like the surface of a rough ocean, the probe was riding the waves on the shore of the galaxy, sometimes in the water, sometimes momentarily in the air, before the next wave covered it again. The expectation grew. Each new packet of data was analyzed with feverish intensity. They knew the moment was near. And then, in the summer of 2012, the pattern changed. The fluctuations stopped. The data became unmistakable and definitive. The flow of energetic particles from the sun, the last tangible trace of its home, the wind that had filled its sails for 35 years, vanished. It dropped by more than 1,000 times, until it became a trickle, and then, effectively, nothing. At the same time, as if a floodgate had opened, the level of galactic cosmic rays, particles born in the hearts of distant supernovae, skyrocketed, reaching the highest levels ever measured. The change was abrupt, unequivocal, and permanent. The lonely traveler was at the threshold. The air had changed. The sound of the river had disappeared, replaced by the roar of the ocean. After 35 years of travel, after more than 18 billion kilometers, the shore of interstellar space was, at last, within its grasp. The moment science had awaited for decades, the main objective of the Voyager interstellar mission, was about to be fulfilled. Humanity was about to finally leave its stellar cradle. The data that arrived on Earth during the summer of 2012 was unmistakable. On August 25th, Voyager 1's instruments recorded the definitive cessation of solar particles and, simultaneously, a massive increase in galactic cosmic rays. For the mission team, the evidence was overwhelming. After 35 years of journeying through the solar system, their creation, Emissary, had crossed the border. It had left the nest. It was a moment of quiet jubilation and profound awe. They had achieved the goal they had set for themselves decades earlier. However, in science, extraordinary claims require extraordinary proof. And there was one piece of data that didn't fit, one last puzzle that kept the world in suspense for almost a year. Theoretical models predicted that upon crossing the heliopause, the final boundary of the solar bubble, the direction of the magnetic field should change dramatically. The sun's magnetic field, dragged out in a spiral, should give way to the galaxy's magnetic field, which is believed to be oriented in a different direction. But the data from Voyager's magnetometer showed no such change. The direction of the magnetic field, though its intensity fluctuated, remained the same as it had measured inside the solar system. This created a deep division and intense debate in the scientific community. Was Voyager truly outside? Or was it in a strange, unknowing border region that no one had imagined? A sort of magnetic purgatory? The lonely traveler had sent a postcard from an unknown place, and those at home couldn't agree on the return address. For months, the team analyzed the data, looking for an explanation. The situation was frustrating. They had two sets of contradictory evidence. It was like being in a dark room and feeling a sea breeze and smelling the salt air. But when you touch the wall, you still feel the wallpaper of your own home. The solution to this enigma, the irrefutable proof, came unexpectedly. It came not from the instruments measuring particles or magnetic fields, but from the probe's ears, its plasma wave instrument. To understand how the mystery was solved, we have to go back in time a year, to March 2012. At that time, the Sun, nearly 18 billion kilometers away, unleashed a massive eruption, a coronal mass ejection. A great wave of plasma and energy began to travel outward through the solar system. For over a year, this wave traveled, crossing the orbits of the planets, weakening but still potent. Finally, in April 2013, this solar shockwave reached Voyager 1's location, and in doing so, it caused the gas surrounding the probe to vibrate, to oscillate, like a guitar string being plucked. Voyager's plasma wave instrument heard this vibration. It detected a tone, a hum in the surrounding plasma, and the frequency of that tone was the key to everything. The frequency of plasma oscillations depends directly on its density. It's a fundamental law of physics. By analyzing the pitch of that hum, scientists could calculate for the first time the density of the material Voyager was floating in. The result was the definitive proof everyone had been waiting for. The density of the plasma was 40 times greater than that measured in the heliosheath. It was too dense to be solar system material. It matched perfectly with the predictions for the density of the interstellar medium. The debate was over. The evidence was unequivocal. The hum of space was the siren song of the galaxy. Voyager 1 had been flying through interstellar space since August 2012. We just hadn't known for sure until the Sun, in a final act of communication with its prodigal son, rang the bell to confirm its arrival. On September 12, 2013, NASA made the official announcement to the world. Voyager has arrived. For the first time in history, an object created by human hands was officially sailing in the galactic ocean. Imagine what that means. The lonely traveler was no longer bathed in the breath of its own sun, but in the matter of the stars. The thin gas that now surrounds it is composed of atoms that were forged in the hearts of supernova, that exploded millions of years ago in suns that lived and died long before the Earth was formed. It is touching the ancient history of the Milky Way. The environment is profoundly different. The cold is more intense. The darkness, if possible, deeper, and the radiation from galactic cosmic rays, no longer deflected by the sun's magnetosphere, is much more intense. It is a harsher environment, but it is the real environment of the galaxy. Humanity had crossed a threshold comparable to that of the first organisms that left the water to breathe air. We had left our small, protected cosmic pond to set a foot, or rather an antenna, on the vast galactic shore. The traveler's solitude had been transformed. It was no longer alone in exile from its own system. It was now a true immigrant in a new cosmic country, a place we know almost nothing about. Its mission of exploration had, in many ways, culminated in its greatest success. It had fulfilled the promise made 36 years earlier. But its other mission, the one engraved on a golden record, the one that did not depend on instruments or data, was just beginning. Now, more than ever, it was a messenger, a silent ambassador in a strange land. Now that it sails in interstellar waters, the lonely traveler has been transformed. Its main purpose is no longer to send data about magnetic fields or plasma waves. That is now a secondary task. Its true mission, the one it will carry out for eons, long after its transmitters fall silent forever, is that of being an ambassador, a messenger, a bearer of a relic, a testament from its creators. Attached to its side, protected from cosmic dust by an aluminum cover, is its heart, its soul, a 12-inch gold-plated copper disc. We know it as the Golden Record. This is not a scientific component. It is a work of art, a time capsule, the most ambitious message in a bottle ever conceived. The idea, again, driven by the vision of Carl Sagan, was simple in its conception and monumental in its execution. If Voyager were ever to be found by an extraterrestrial civilization in the unimaginably distant future, what should it say about us? How could we encapsulate the entirety of a world's experience in a single object? A committee led by Sagan and writer Anne Druyan faced this nearly impossible task in a whirlwind of activity during the spring and summer of 1977. They had only a few weeks to compile a portrait of humanity. The choice of format, a phonograph record, may seem archaic, but it was a deliberate decision. The information is physically engraved in its grooves. Unlike a digital format, which could become unreadable over time or require specific software, a groove is an incredibly durable way to store information. It is a fossil of sound and image. The disc itself is made of copper and plated with a layer of pure gold to protect it from the erosion of space for billions of years. Along with the record, a needle and cartridge were included, the tools to play it. But how would an alien civilization know what to do with it? The record's cover is, in itself, an instruction manual. It is an engraved diagram, a language of symbols based on science, which is hoped to be universal. In the upper left corner, there is a drawing showing how the record should be played, with the needle and the correct rotation time, defined in relation to the fundamental frequency of the hydrogen atom, a universal constant. Below it, there is a star map. This is perhaps the boldest and most controversial element. The diagram shows the relative position of our Sun to 14 pulsars, rapidly spinning neutron stars that emit radio pulses with incredible regularity. Since the frequency of each pulsar decreases at a known rate, this map not only pinpoints our location in the galaxy, but also the moment in time when the craft was launched. It is an address and a postmark. It was an act of immense hope and vulnerability, risking revealing our location in the hope of finding companionship. And inside, in those golden grooves, is the content. First, 115 images encoded as audio signals. The images were chosen to show an honest view of our world and ourselves. They begin with the basics: diagrams of our solar system, our DNA, human anatomy. But they quickly move on to everyday life. There are images of Earth's landscapes, deserts, mountains, forests, and oceans. There are photographs of plants and animals. And then there is us, an image of a group of people of different ethnicities, an Olympic runner, ballet dancers, a woman licking an ice cream cone, a man eating a grape, an image of city traffic. It is not an idealized portrait. It is a portrait of who we are, with our complexities and contradictions. Next come the sounds of Earth, an audio collection that attempts to capture the symphony of our planet. It begins with the sounds of nature: wind, rain, thunder, birdsong, the call of humpback whales. Then it moves on to the sounds of life and humanity: a heartbeat, footsteps, the sound of a blacksmith at work, a dog barking, a baby crying, and laughter. The sound of a kiss was included, and a mother's first words to her newborn child. They are the sounds that define the experience of being alive on our world, beyond any language barrier. And of course, there is music. 90 minutes of music, an eclectic selection designed to show the emotional and cultural diversity of our species. It begins with the first movement of Bach's Brandenburg Concerto No. 2, a piece of mathematical complexity and beauty that represents perhaps the pinnacle of human intellect. But the musical journey spans the entire globe. There are initiation chants from African pygmies, percussion from Senegal, handpipes from the Solomon Islands, a wedding song from Peru, and there is also more modern music, the blues of Louis Armstrong, and the rock and roll of Chuck Berry with Johnny B. Good, an explosion of youthful energy and optimism. The selection is a testament to our ability to create beauty, to express joy, longing, and sadness through the universal language of sound. Finally, the record contains greetings, messages of goodwill in 55 languages, ranging from the dead languages of antiquity, like Akkadian, to the modern languages of the world. A child says hello in Spanish. The then Secretary General of the United Nations, Kurt Waldheim, recorded a message of hope. The English greeting, spoken by Anne Druyan, simply says, "Hello from the children of planet Earth." The overall message is one of peace and friendship. An attempt to put our best foot forward to the cosmos. As the committee worked feverishly to compile this greeting, they realized something profound. The probability of this record ever being found was astronomically small. The true audience for this message, at least for the foreseeable future, was ourselves. The act of creating the golden record was an exercise in global self-assessment. It forced us to ask, who are we? What do we value? If you had to summarize all our history, all our art, all our science in a single object, what would you choose? In this sense, the record was not just a message for extraterrestrials. It was a message for the future of humanity, a reminder of who we were at a particular moment in our history, a moment of great hope and audacity. Now, that record, that fossil of a moment in time, travels silently on the side of the loneliest pilgrim. It is a testament that on a small world, in orbit of an unremarkable star, a curious and sometimes conflicted species looked at the stars and, instead of fear, felt the desire to say hello. The bottle has been cast into the ocean. Now, only the journey remains. Our journey together is coming to its end, but Voyager 1's journey is, in many ways, eternal. Today, at this very moment, the probe is more than 24 billion kilometers away, a figure so vast that light, the fastest thing in the universe, takes more than 22 hours to cross that chasm. It continues to travel at a breakneck speed, moving about 540 million kilometers farther from us each year. It is immersed in the interstellar medium, an environment of unimaginable darkness and cold, a place where the sun is just the brightest of a million stars. It is still alive, still speaking to us, but its voice is now an incredibly faint whisper, and we know that soon it will fall silent forever. The lonely traveler is slowly dying. Its life comes not from solar panels, which would be useless in this darkness, but from the dwindling heat of a plutonium-238 sphere. This radioisotope thermoelectric generator has been its heart for nearly half a century, but the radioactive decay that powers it is a clock that cannot be stopped. Each year, its power output decreases by about 4 watts. 4 watts may not seem like much, but it is the difference between life and death for its instruments. For years, engineers on Earth have been making difficult decisions, acting like doctors managing the energy of an elderly patient. One by one, they have been turning off the heaters for the instruments. First those for the scan platform, then those for the particle detectors. Each instrument that is turned off is a small death, a sense that the probe loses forever. It is an act of conservation, an attempt to keep the most critical systems, like its radio transmitter, alive for as long as possible. Voyager is conserving its breath, entering a deep and prolonged hibernation as it ventures ever deeper into the galactic night. It is expected that sometime in the late 2020s and potentially into the 2030s, power will decline to the point that instruments must be shut down one by one until only the carrier remains. The flow of data that has taught us so much about the universe will cease. And sometime, perhaps around the 2030s, the day will come when there is not even enough power to keep its antenna pointed at Earth. Its voice, the faint whisper we have been listening to for over 50 years, will finally fade into the background noise of the cosmos. On the screens of the Deep Space Network, its signal will simply disappear. There will be no explosion, no dramatic end, just silence. It will be the end of our conversation, but not the end of its journey. Because Voyager 1 will keep going, Propelled by its own inertia, it will continue its trajectory through the Milky Way, essentially forever. It is a ghost ship on an eternal mission. It is not heading towards any particular star, but calculations show that in about 40,000 years, it will pass at a distance of about 1.6 light-years from a small star in the constellation of Camelopardalis, called Gliese 445. By the time it gets there, the star will have moved, and Voyager will continue on its way. Its final destination is to complete an orbit around the center of the Milky Way, a journey that will take it over 225 million years, accompanying the stars in their majestic and slow galactic dance. It will outlive its creators. It will outlive the species that built it, and quite possibly the planet that launched it. It will become a wandering fossil, an artifact of a civilization that once existed on a small blue world. It will float through geological eras, witness the birth and death of stars, and continue to carry its golden message, an echo of Beethoven, of whales, and of a child's laughter through the immensity of time. It is the most enduring legacy we have ever created. And so the story of humanity's loneliest journey is ultimately a mirror. It is a reflection of our own loneliness in the cosmos, but also of our insatiable curiosity. It is a testament to our ability to dream beyond our limits, to send a part of ourselves to a place we can never reach. Voyager 1 is the embodiment of the noblest part of our spirit, the one that explores, that seeks, that yearns to connect, even across an abyss of silence and time. Its long journey through the night is a reminder that every life is a journey, often lonely, full of fleeting encounters and long crossings. And in the end, what remains is the message we leave behind, the echo of what we were. Now, as you prepare for your own journey into the silence of the night, into the world of dreams, think of our little traveler. While you sleep, it is still out there, sailing in the darkness on your behalf. A point of human consciousness, a silent testament to a day when we looked at the stars and dared to take the journey. The journey continues, always calmly, always at the pace of the universe.